All right. So a couple announcements today, actually more than normal. We are going to be continuing rotational motion. That's the concept we started last time, and we're going to keep working on that. We're going to practice some of the kinematics things we worked on before, having you do some more with that worksheet 1 that we started last time. And then we're also going to be adding in the concept of torque today, and probably just briefly introduce the idea of moment of inertia or rotational inertia. That's the goal for today. In terms of assignments, the positive physics unit 10 assessments due tonight. So make sure you're getting that completed by midnight tonight. And then that's the one on uniform circular motion that we've already learned all the concepts for. And then 15 and 16, those units are due next week. We don't have school Monday, or you don't have school Monday. So Tuesday is when 15 is due. And it is a little bit longer one, so you probably don't want to wait till Monday. You probably want to kind of click away at it little by little. And then, and actually it's on torque, which is what we're going to start learning about today. And then 16 is due the next Thursday, or next week on Thursday. It's much shorter, so there's just the one class period between instead of a double time frame. And that Thursday should be the last day we need for rotational motion. So that's the plan. So that's what's coming up. I don't really anticipate giving you any other formal assignments. We'll be doing a lot of work in class and working with some of the worksheets. When we start working on the worksheets later, if you guys haven't picked them up, everything we're doing this week is over there on that side counter. And so you can grab those if you haven't. But the other announcements for today, I did add the AP test schedule to the news section of the bulletin board page on Axis. So if you look at the bulletin board page down towards the bottom, it says news, and one of the items is AP test schedule. There's 3 dates, but Oaks is only going to support the first one and the last one. The middle one actually falls right during exam week here at Oaks. So it would just be impossible to be trying to proctor those AP tests and the regular exams. And so we're not going to be able to support that date. So our plan will be to continue to prepare as we have been to take it on the 5th. And on May 5th, that is an in-person on paper version. That's all they're offering on that date. And so depends on how the world changes between now and then. It may be that pretty much everybody feels comfortable and confident doing that, and you all come and take it in person. It may not be. No one could have predicted the way the world would be right now, and so we can't really expect to predict what it'll be like in May either. So if things continue to improve, probably the majority of you will take it May 5th. If maybe your health doesn't improve, or your family situation is such that it's not safe, or the world situation declines, who knows? Any of those things could make it where May 5th just doesn't feel like the better choice for you. And if there is a reason like that for May 5th not fitting your schedule, or maybe it's because you have another AP exam on that same day, because that's AP Physics 1's not the only one that's on the 5th. It's just that's when it is. But there's other exams that day as well. So if that date doesn't work, they will be sending out, probably from Miss Davis or Mr. Lindsay. I think those will be the 2 people that will be sending out the email. And I expect it'll probably come either this week or next week with some clarification on if you can't take it on May 5th, then you would fill out a form and say, here's why I can't take it, and I'll be taking it on the 9th. And the 9th is obviously after the school year is over. I think students are done either like May 30th or June 1st or something like that. So you'll be done with school by then, but it's an at-home online only version if you take it on the 9th.
Mm-hmm. So on May 5th, do we have classes that day?
Well, some classes meet, but we won't, because you'll all be taking the test that day. So.
Oh, okay.
Welcome back. So yeah, during the AP testing, I don't know how it's going to work this way. Traditionally, if you have an AP test, you don't have to go to your other classes that day. I don't know if they're still going to honor that same sort of strategy or whatever that they've had in years past, or if they're going to make a different change to that. But that's what it's been in the past. So, and we definitely won't have class that day. I think if I remember correctly, it's at noon, so it's the afternoon test. It's either noon or 1, I believe. And so if I don't know if that's an A day or a B day, I can't remember. But if it happens to be the day that we normally meet, I'll be free. So I sometimes will have students come in anyway, even though we don't have class, and they'll just ask questions or like, hey, I was trying to figure out this FRQ. I don't understand the scoring guide. Or so I'm kind of office hours sort of thing, but we won't officially have any class that day.
Neat.
The other announcement is that if you are not a senior, which most of you that fits, then you probably, many of you would be wanting to take other AP or honors classes next year. And if you want to take AP or honors classes, you have to get a recommendation. So I can't give a recommendation outside of the science department, but if you are wanting to take an AP or honors science class next year, also on Access on the bulletin board page in that same news section, it's got a thing that says AP honors recommendations. If you click on that, there's a place where you can click on a link to a form. When you click on the form, all you have to put in is your name, and then it's just got like a click box of all the classes you could choose from. And so if you know you want to take AP Physics 2 or AP Bio or something like that, you can just type your name in and click that class, and then I'll get a report saying, Ethan has requested that you support his decision to take this class, and then I can go into Access and give you the recommendation. So if you need a science recommendation, I'm happy to do that. Just use that form, and then I'll see what you need, and I can change it or adjust it for you. I pretty much went through, I hope I didn't miss anybody. I tried to do it by memory, but I pretty much went through and tried to pick everyone that wasn't a senior that is in AP1 and go ahead and put you in AP2 already. If I missed you and you want to take AP2, let me know. Can you see what you've already been recommended for on your side of Access?
No, I haven't even
You
checked.
can't? Okay. So if you just go ahead and fill out the form, and I can double check, but I'm pretty sure I got all the underclassmen already approved for that. But I didn't pick anything else because I don't know if your interests lie in chemistry or biology or marine biology or anything else. So I didn't pick anything but physics 2. So make sure you do that if you want a recommendation from me. You may have already talked to other science teachers and have that ironed out, but if you need it from me, let me know, and just use that form. And then the other thing is tonight there is a STEM spotlight that's sponsored by the Oaks Guidance Department. And it's actually, they have a guest speaker from the USC Department of Engineering. And that person will be talking to you, not just about USC's engineering department, but engineering in general as a career, what career choices there are, what are some new hot fields of study and career paths in engineering, and not just engineering only, but also other STEM areas. They're also going to talk about if you're wanting to go to college and pursue a STEM or engineering career, what should you be doing in high school? What classes should you be taking? And then also talking a little bit about the admissions process in those kinds of schools. If you want to go in and enroll as an engineering student, how can you make your application and resume and stuff look good for them in that process of them choosing students? So it's supposed to last about an hour. That is also on Access, but instead of in the news section, it's in the top right in the announcements, because then it's after it's over, it'll just disappear. So that's tonight. It's at 6 p.m. It lasts about an hour, and it's just basically there's a Zoom link on the announcement on Access. Just click on the Zoom link, listen in, learn from the expert from USC on about STEM careers and especially college preparation. So, any questions about any of those? Lots of announcements today.
So
Making sense? All right. Well, what we're going to do first before we start learning about torque and rotational inertia is review a little bit on rotational velocity and acceleration and motion maps. So if you'll get out worksheet 1 that we were working on before, and if you want a print copy of it, if you were home before, there's all the worksheets are over here. So you're welcome to grab those. We'll be looking at some examples from worksheets 2 and 3 in the future as well. All right, for worksheet 1, we went through number 1 together, and hopefully you completed that as we discussed it, whether you just wrote some notes in your notes or whether you had a copy of the worksheet and actually were following along that way. Hopefully you completed that one and have a good understanding. Did we try number 3 in this class? I can't remember if we got that far. I don't think we did. Yeah, we did.
I remember us.
We did do 3? Okay, all right, good. That's good. They ran a little further than I thought. We did not do number 2 or 4 because 1 and 3 are similar. They give you the position time graph, and then you have to come up with the velocity time graph and the motion map and the words 2 and 4 are kind of flip-flopped. They give you the velocity time graphs, and you have to come up with the position time graphs and come up with the motion maps and such from there. So let me share the screen here and make sure you're looking at the right questions, and then give you a little bit of a hint. And then for those of you that are in Zoom, we'll put you in a breakout room and have you guys discuss 2 and 4. And then you guys in here will kind of have you pair off and meet with people that you're nearest to and just talk through plexiglass to discuss those questions. Make sure we're on the right track. And like I said, to give you a real slight hint here. That's too much of a hint there. Yeah, it looked quick enough. You got the whole answer. All right, so we did number 1. Number 2. One thing I want you to notice is when we drew number 1, when we drew the velocity time graphs, all the lines were straight horizontal lines. Right? They were all constant velocity. It was either a constant positive or a 0 or a constant negative velocity. What you're going to notice when you do numbers 2 and number 4 is they have some straight lines, straight horizontal lines, and then they have some straight diagonal lines. And so those diagonal lines mean that the velocity is changing, right? It's going from some value to a new value. So that means in your position time graph, you're going to have some curves instead of just straight lines. All right, so I want you to work on numbers 2 and 4. So, Kyle and Nat, you guys are right beside each other, so you can just kind of chat through, you kind of work on your own, talk, help each other out. Ethan and Cade, Johnny and Jack over there, and you two guys, Andy and Evan, you can work here as well. Just kind of, you can work on your own as much as you want. You can chat and help each other as much as you want. Give you about 10 minutes, and hopefully at least you'll compare notes when you're done and see if you're agreeing on numbers 2 and 4. For you guys in the Zoom, let me go ahead and put you in a breakout room so you can more easily converse and interact and do the same. So any questions about what to do?
Wait, there's a chance to let people choose their own rooms?
Yeah.
Man, I didn't do that. That's cool.
I figured that would be too unbalanced. We'd have some rooms with a whole bunch of people and some rooms with nobody. And so.
True.
All right, so go ahead and see if you can figure out numbers 2 and 4, and I'll get you attendance posted.
So start off with negative.
Looks like it's starting out with a negative.
Wait, technically it should be going because it actually no, because it stays.
And then it's increasing. And then it goes into a positive velocity. Yeah, wait.
Because it had a negative velocity right now and it's staying there and then it
That was
accelerates.
negative.
Yeah, but the velocity is negative, so like this would be going down.
Oh, you're
I
right.
think it is.
Yeah.
Not that far.
I think it's wrong. It looks the same.
Oh,
We had to have it
no
going
problem.
straight first, right?
Um,
Because velocity is constant. Oh, wait.
I usually use machine seconds. They don't really tell you, but that makes it.
Yeah, I
got it.
Scale.
Oh, very here. I think it's gonna go.
But then it's like.
All right, yeah,
Still
that's
going
fine.
down, but in that, like, it's
At a
like
faster rate.
long.
I just want to reference other
Arrow
stuff.
starts increasing and it stops at 5 and then it turns around at like 6. and goes-
We know it's
I
starting
think
to
it's
go
gonna
up.
start out like number
Does it
3,
curve?
because with this one, it's negative, then it goes to even and up like this one. It's negative, then goes even up. So I think it's gonna start
Yeah, I think that's right.
positive and then.
Yeah.
Okay, so
That
this,
looks-
this
I think
one,
it is.
so this one's a curve. So start positive. So velocity.
Yeah, I think this works.
So
As long as these two are straight, then this and this are straight. and then-
Have this included. All right, so I'll have some of you in the Zoom and those of you in the classroom kind of taking turns explaining and showing some things. If you're in the classroom, I've tried to focus the camera for those on the Zoom on the screen. I'll maybe zoom it in just a little bit more, but that way you can actually come up and write on the screen. So if you just choose the pen, you can either write with your finger or you can actually use one of the pens that is magnetized to the board and just draw on here for us. For the written descriptions, I think we'll just have you read what you wrote rather than try to write that on the screen.
You're frozen.
Yeah, they're not really frozen. On here they are. As soon as I turn the pin on, it freezes it here, but they're still live. I can see them moving over here. So yeah. Sally and Aiden, you're both still alive, right? You look alive. Okay, good. All right, so for number 2, Aiden, could you just tell me, what did you have for your written description? What did you think about for this one?
I think I put when for velocity, it changes when like the line like is like diagonal, but like when for the part it like when it curves, that's when the velocity changes. And then
Okay.
for position, I said I think I put that it like changes every time when it just moves. Like for the horizontal parts, like it just like it's not like I mean it's like moving, but it's not like changing velocity, so it wouldn't be changing position. And then for acceleration, wait, did I put it for acceleration? Oh, for acceleration, I think I said that when, wait, I'm not actually sure for acceleration on this. I don't think.
Okay. That's all right. Centripetal acceleration, we're going to hold off on anyway, but for angular acceleration, when is the velocity changing? It is in the first part or the middle part or the last part?
The middle part, because it's a diagonal line versus horizontal. So
yeah,
acceleration would be changing then.
Yeah, so that's when we have that acceleration is in that middle part. Good. Can I get a volunteer here in the class to come up and draw how you interpreted that position time graph on there for me? Someone to do that? Thanks, Nat. Like I said, you can either use your finger or you can use the pins that are magnetized to the bottom of the TV there. Oh, I meant, oh, you can do that. We can go to the math motion. I was going to have you do the other one first, but if you want to do the motion map, that's fine.
Oh, I can do that one.
Okay. All right, good. Can you just talk us through a little bit of how you were thinking that through?
Because the object at first is like the line, it's under the line, so it's going backwards or at a negative velocity. And then as it's changing, meaning it has to have a curved line. And so it curves up into the new positive velocity.
Good. Yeah, very nicely done. Any questions about the position time graph for that one? You don't really have a scale to know, exactly at what second things happen. And it is tricky to draw. It looks like your sleeve was probably catching the screen there. It's actually a multi-point touchscreen, so you can draw multiple things at once. So you have multiple students drawing at once. But if your sleeve hits it or another finger hits it, you leave stray marks. But yeah, nicely done. And then I think the motion map's pretty hard to draw on that screen. So I think what we'll do is just I'll show you what they came up with. I also want to show you one little detail that they have on their version of this. Get it shared here. Oh, actually, I think it'll probably go right away if I just turn this off. We're just gonna delete all that hard work that Nat put up for us, but you can see the picture that they have on the key is virtually identical to what Nat had there. But there's one slight little detail that they made a note of, and I don't know that I would have even thought necessarily to be that precise, but I think it's pretty cool that they did. If you think about it, the zero velocity where it's crossing the x-axis, that should actually line up with the very bottom of that curve, because that's when it's technically changing direction, right? So they drew an additional little like dashed line. I don't know if you can see it real clearly on the screen, but they drew kind of a little light dashed line to show that that peak, or the valley, I guess, the upside down peak, the valley of that curve should match with that time when it's crossing the axis. In terms of how steep you made your lines, it's ideally you'd want to make the first segment steeper and the last segment less steep. it's really tricky to sketch these things when you don't have actual scale. But you can see that I actually thought that Nat's job on the graph was better than theirs in terms of showing that clearly. Theirs look almost like they're pretty much the same slope, just one's positive, one's negative. I thought she did a nicer job of making the second one look less steep on the slope. But at least you can see the shape. So any questions about that? On the motion map, I'm gonna show you what I sketched out. Theirs is kind of hard to read. Mine might not be a whole lot better. But what I did is, we know that initially it's moving in the negative direction. And it's moving pretty fast because it's fairly steep. I don't think I drew mine as well as Nat did in terms of, I should have made my last segment a little flatter than that, but I've got long arrows initially in the backward direction, and I just made it like 3 seconds, 6 seconds, just to kind of give myself a point of reference. And so I have kind of 3 long segments, and then it starts slowing down, but still in negative direction. So then I show some decreasing length arrows, and then at 6, it's really, in a motion app, it's hard to show that transition of exactly where it is changing direction, because it's kind of between seconds. I suppose you might be able to estimate maybe it's at the 5th second, but since there's no scale, it's a little bit hard to know exactly when it's changing direction. So that doesn't show up on the motion map too clearly, but we do know that by the time we get to the 6th second, it's actually going back the other direction. And I just tried to make those last 3 arrows about the same length as each other and shorter than my initial ones. So really the pattern is what we're looking for on motion maps, to see if you're really recognizing that you have the direction identified correctly. And at least relatively speaking, are you showing longer arrows or shorter arrows appropriately? In terms of scaling, they didn't give us a lot of detail, so you can add some in if it helps. But any questions about part 2? All right, let's look at number 4 then. Sally, could you tell us what was your written description for number 4?
So it starts at rest for 2 seconds, and then it starts rotating clockwise and accelerating in the positive direction, and then it starts accelerating in the negative direction and still rotating clockwise.
Good. And then can I get a volunteer if you want to draw this in for us, Ethan? Just the little arrow, there's like, it's not the top one, it's the bottom little arrow there that'll turn the pin on.
It's like the screen gets darker too.
Mhm. All right, good. And Sally and Aiden, can you guys see that okay on the screen there? Okay.
Yeah.
Good. That's virtually identical to what I put on mine. We've got a flat segment in that first time frame, because at that point it's motionless. We don't really know the position, so you could make it at 0, you could make it higher, you could make it lower, because we don't know the position from the velocity time graph. But we do know that it's not changing position in that first time frame, so it should be horizontal with no position change. And then the position is going to change in an exponential fashion. It's going to be accelerating, so you should see a curved shape where it's getting faster and faster, because the amount of position it's changing per time is increasing as the velocity increases. And then suddenly at that 4-second mark, we should start to see a shift from, instead of increasing speed, to decreasing speed, but still in the positive direction. And so we see kind of that S-shaped type curve there in that last, from second 2 to second 8, showing that change. But any questions about number 4, the position time graph? I'm curious to see what they're going to do this year. I have a feeling, and this is just my intuition or my suspicion. I have a feeling, because they're able to do paper tests this year, at least right now, they're planning to be able to do paper tests. that they're going to ask you to do a lot of graphing in the pre-response questions. And I could be off base, but when they had it online only last year, that was the thing that a lot of the physics teachers and the people who were writing the test felt limited by is, okay, an online question, it's hard to ask them to graph something. And so I almost have to say, well, can you describe the graph in words, which is tricky. So I have a feeling they're going to feel like the shackles are off. And so let's make them graph everything. I don't know. I could be wrong, but I suspect that could be.
I have a good feeling that's gonna happen.
All right. So now motion maps, we'll go ahead and look at the motion map. The motion map is really more of a, this curriculum has the philosophy that if you can actually map that motion out that way too, it just helps your mental development and grasp of the concept. Motion maps are not technically a College Board thing. So they're not going to ask you to draw motion maps, but they would very likely ask you to do graphs.
Yeah, the motion maps are a little unstandardized.
Yeah, for sure. All right, so let's look, I'll show you my version of the motion map for number 4. So again, we do have some scale here actually for number 4, so that helps. And you can see my graph is kind of similar to Ethan's there, trying to show that S-shaped sort of curve. But I just showed a few seconds where my time is 0, then 1 and 2. So I got a 2-second time frame where it's not moving, it's just staying at that same angular position. And then for the next 2 seconds, it's going at a small velocity, then a bigger velocity. And then at the 4-second mark, it's going at its maximum velocity. But then after the 4-second mark, it's going to start decreasing. So by the time we get to 5 seconds, it should be going a smaller velocity, so a shorter arrow. And then 6 is shorter, and then 7 is shorter. And then when we get to 8, we're at 0. And so there shouldn't be an arrow on the 8th dot, because this one you actually see it hitting the 0 at 8 seconds. So that one actually is a little bit easier since I gave us some scale. But again, motion maps are more part of this curriculum's logical thought process of, hey, we need to challenge students to think about motion in a variety of ways. Whereas I've never seen College Boards, I will say they have some motion maps drawn and you have to interpret them, but I've never seen them ask you to draw a motion map. And in fact, when they draw them, they don't call them motion maps. They just say this sequence of dots represents the position of an object over time. And this sequence of dots represents the position of a different object over time. And so they really are showing you motion maps. They just don't call them that. And I've never seen them ask students to draw it. So it's not a bad thing to practice, because if you can draw it, then you can for sure interpret it. So questions about this worksheet so far?
Sure.
All right, we're not going to do 5 and 6 together. It's more of the same. I mean, you can practice them if you would like, and I can check them over for you if you'd like. But the last page is what we're going to work on a little bit on Thursday. You can see the last page has a bunch of word questions, and those are all using the kinematics equations with the angular variables. So solving for omega, solving for theta, solving for alpha, using all the notes we took last time and actually plugging some things into those equations. So we'll practice some of those on Thursday. But today I want to go ahead and move on to the next topic. So let's switch gears again. All right, so I mentioned this last time, but I saw in some students' eyes that light bulb look of, oh yeah, that makes sense. And I saw other students' eyes of, the weekend is almost here, and I wasn't sure it was really sinking in. So I thought it might be a good thing to touch on again. There are 3 types of acceleration, and the first one we learned was really linear. We only learned it linear, and it's translational is a more generic term for that, where it's could actually be moving in a circle, but we're talking about how its speed is actually changing over time. And usually it's linear. For this class, it would only be linear. Because when we talk about circular motion in AP Physics 1, it is limited to uniform circular motion, which means the speed is constant and the radius is constant. So we would only be applying this in linear scenario. Technically, if we were to the next level, like AP Physics 2, at that level, then we can start saying, well, now let's look at not uniform circular motion, but any circular motion. We can't actually have an acceleration Hey, Rocky, glad you were able to get back online with us. I know you missed the discussion and we just finished the worksheet a few seconds ago. So, but you could go back and watch that portion of the video when I post later if you want, and see if you kind of check your work. If you were able to converse with Sally and Aiden, you're probably on the right track because they seem to be on the right track too. But if you want to see that, you can look at that 10-minute segment or so on the video. So that's the first kind of acceleration. That's the first kind that we talked about. We use the variable A and it's changing velocity over changing time. All right. The one that we learned last week is angular or rotational acceleration. And that is where the rotational speed is what's changing. And so instead of A, we use alpha, and instead of V for velocity, we use omega for angular velocity or rotational velocity, but still per time. So for the first kind of acceleration, we're going to have units of meters per second squared or meters per second. And then for the second type, we're going to have radians per second or radians per second squared. But then the third kind of acceleration that we learned about is centripetal. And it has no direct overlap. You can't just easily convert. So let's actually go back a step here. Does anybody remember how we can convert from the angular acceleration to the linear?
Multiply by the radius, right?
Yeah, multiply by the radius. We'll review that here on the next slide, but you can take those angular values like acceleration, like velocity, and you can convert them to the linear forms by multiplying by the radius. There is no same kind of situation for centripetal acceleration where you can just simply multiply something by it to get the angular or get the linear. It takes more steps than a simple use the radius kind of a thing. There are relationships because the centripetal acceleration is the tangential or linear speed squared divided by the radius. So it's not that there's no correlation, but it's not quite as simple of a relationship as what we see between the others. And for sure, you cannot interchange these things. So if you know the acceleration A, you cannot plug that into a centripetal acceleration formula. If you know the centripetal acceleration A sub C, you can't plug that into an angular acceleration formula. Okay, they are not interchangeable because they're all measuring something different. And the first one and the third one both are meters per second squared. So they do have the same units, but they mean something entirely different. The centripetal acceleration is how much the direction is changing for the object. Because in uniform circular motion, the velocity's speed is constant. And so it's just the direction of that velocity that's changing to make it go in a circular path. And so the centripetal acceleration is the acceleration that force causes, whether it's tension or gravity or friction or whatever it is. It's the acceleration that the force causes pushing the object back to the center and how it accelerates towards the center. And it is related to the speed that it's moving at in a linear fashion, but it is not the same as the linear acceleration. That's one of the reasons why in this curriculum, they typically will use the units newtons per kilogram for the centripetal acceleration to indicate that, yes, technically it's meters per second, but it does mean something different. All right, so here is that equation that Ethan and Evan both mentioned where we can convert back and forth. And here I want to emphasize and clarify what I meant when I said radians are unitless. So one of the relationships we talked about was you can take the radius times the angle, and that will give you the displacement in a linear amount in meters. So what we would really be doing, what I put here in red is the units of this problem. We would measure the radius in meters. We would measure the angle in radians. But when we multiply meters times radians, we don't get an answer in meter radians. We just get it in meters. Because radians, remember, it's a ratio, it's a unitless value. So when we multiply them in these equations, the radians sort of disappears. And that's why I was saying, understanding that it's unitless can help you figure out the dimensional analysis and the units of your problem solving. The second one, and these are the three that kind of go hand in hand, you can take the radius times any of the angular values and get the linear corresponding value. So the radius in meters times the angular velocity in radians per second doesn't give you meters radians per second. It just gives you meters per second. The radians disappear because they're unitless. And then the third one that we learned last time, if you take the radius times the angular acceleration, then that meters for radius multiplied by the angular acceleration in radians per second squared, the radians vanish and we end up getting our linear acceleration in meters per second squared. So I can turn off this autofocus now so they can see your face.
I go to the bathroom.
You may want to prompt the door open because it automatically locks. So a quick review of those equations, quick review of the rationale behind the equations, and also the fact that radians are unitless and how that sort of shows up in a math-based calculation. Any questions for me on that connection? A couple of slides to sort of review the things we were learning last Thursday. All right, so now on to the new. Torque is the main concept we're going to focus most of our time on today. And torque is a word I'm sure that you're all somewhat familiar with. You could probably all use it in a sentence appropriately. You may not necessarily understand all the physics behind it or the math that connects to that physics behind it, but you probably have a sense about what it means. I'm going to kind of prove to you that you probably have some sense to what it means, and also sort of conceptually generate the equation we use to calculate torque. So if you were trying to tighten a bolt or a nut on a bolt, if you were using one of these three wrenches, you had to choose between them, and you were limited in how much force you can apply because your force that you're strong enough to apply is just the same, right? You can apply that much force now, it's the same. You're limited on how strong you are, but you can choose the wrench you want. Okay, so the force is constant, but you can choose the wrench that you want. So, Rocky, any idea if you could choose any of these three wrenches and apply the same force, which one would you want to choose to be most effective? The top, middle, or bottom?
Probably the bottom.
Probably the bottom. How many agree with what Rocky says? Okay, quite a few hands raised. All right, so if we choose the one on the bottom, you probably, could someone give me an explanation for why? Yeah, Johnny?
Where you grip it on the wrench, or I guess you can say the arm is farthest from the pivot point out of those three. So you have the most torque, I guess you can say, or most applied force.
Yeah. Ethan?
Leverage, so you have to go a longer distance, like the radius of the circle you use with your hand is longer, but it increases the force because you spread it out over a longer distance.
Yeah, so here's one slight thing I would change in what you said, and it's just one word. It doesn't actually increase the force, it increases the torque.
Yeah.
Because your force, in this case, we're saying you're limited on the amount of force you can create, but the effectiveness of that force increases. And when we talk about torque, in a way, we're kind of saying the torque is sort of like the effectiveness of the force we're applying in causing rotation. All right, so they're kind of corollary. They're kind of, we've talked about like there's linear velocity, there's angular velocity, there's linear acceleration, there's angular acceleration. Well, there's force and there's torque. It's not quite as clean of a connection. Like you can literally take the VVAT equation and make it WEWAT. Like you can literally change the V's to omegas. You can't just say, well, torque equals MA. That doesn't work. Okay, so they're not quite as integrated, but they're definitely kind of the closest correlation between rotation. And so that's why when you said it, like in your brain, I know you're thinking the right thing because you're thinking, oh, I'm more effective. I'm using that force and capitalizing on it best. The word that I want you to connect with is I'm using the same amount of force and I'm increasing the torque, so I'm more effective in rotating it. So what we're really doing in this case is thinking about the length of the lever arm. And that's the one word that Ethan used that I will often refer to as the lever arm. And Johnny did a nice job of explaining, you can have a short wrench and push it on the end, and you can have a long wrench and push it close to the middle, and you could still be more effective with the shorter wrench if you push it further from the center. So you start out where you push it really matters, not just the length of the wrench, right? You can have a really long wrench, but if you don't push it out on the end, you're not gaining the effectiveness of that long wrench. You may have even seen people like put a pipe over the end of a wrench to gain more leverage. So this is the use of leverage by lengthening the lever arm, which we measure as R in terms of a variable, and we're going to measure it in meters. So the greater the lever arm, the longer the lever arm, the more effective it is, just like Rocky predicted and like many of you believe would be true. So again, you kind of have a sense about what we mean when we say torque, and based on your experience, you probably have a sense of what you need to do to capitalize. All right, here's the easy one. So that was middle level difficulty. All right, here's the easy one. So same wrench, but you can either apply a little force or a medium force or maximum force. Which one's going to be most effective? Yeah, this is like the easiest question, right? You're never going to see that on an AP exam, but it's, yeah, you wish, right? It'll take a few of those. But in this sense, it's pretty obvious. We want to apply the most force we can. But what they're trying to highlight here is not only do we have a sense that you need a long lever arm to maximize it, you obviously want to apply as much force as you can as well, because the force does matter as long as you can apply some. The more force you can apply, the more effective it will be. So clearly the amount of force you apply and the length of the lever arm both make a difference. They both impact your effectiveness in applying or creating torque. Right? Now here's a little trickier one. Some of these are really easy. Some of these are not so easy to figure out exactly which ones would be most effective. So there's 5 examples on how you could push or pull on this wrench to try to maximize your effectiveness. Now there's a couple that are really easy. So can anyone identify a couple here that would definitely not help you out? Andy?
The third one.
Which one's the
Like
third one?
1, 2, 3, like in the middle of the 3.
This one?
Yeah.
This one would not help.
I don't think so.
Yeah, I agree. I agree. If I pull the wrench this way, I have just dislocated the wrench from the bolt, right? That's not helping at all. Yeah, Nat?
The second one pushing it in.
This one?
Yeah.
Yeah. I mean, I can apply a whole bunch of force, but that's not going to spin the nut or bolt at all. It's just going to push on it. So these would be clearly highly ineffective. All right. Any other ideas? Yeah, Johnny?
Maybe the first one at the top left.
Okay. Why would that not be so great?
Well, you're kind of doing the same thing you did in the one below it. You're pulling the wrench away from the direction that it needs to go, so it kind of defeats the purpose.
Yeah. So a little bit of the force is going to start to spin it, but pretty soon the wrench is just going to come off the bolt,
Yeah.
right? I'm not really effective with that one either. So those 3 are usually pretty easy to identify. Yeah, those 3 aren't going to be helpful. It's the last 2 that sometimes can be a bit tricky. Kyle, what do you think? Would you think pushing at an angle would be better or pushing straight down would be better?
Probably an angle.
Think an angle?
Yeah.
Okay. Kate, what do you think?
I think straight down.
You think straight down?
With the angle one, you're sort of pushing into the bolt. And I don't know how to explain it, but if you see like the sort of components of the force, there's the force that's pushing into the that bolt.
Yeah. So I don't know if you could hear that. I'll restate it because we had some noise coming in through the door there. So Kate was saying that with this bottom one here, where it's at an angle, it's some of that force is pushing into the bolt. And so he was saying that wouldn't be quite as effective. Aiden, what do you think?
For which one? Sorry.
Would you think pushing at this bottom one here on the left at an inward angle, or the one over here on the right pushing straight down? Which one do you think would be best?
I think I'd say pushing straight down would be
Okay.
better. I'm pushing to the side wouldn't be like bad, but I think just to maximize the force, I think straight down would be better.
Okay. Sally, what do you think?
Yeah, I think straight down as well. Because
Yeah.
as Caden was saying, I think you would be putting force where you don't want it to be. I think it would definitely be maximized just putting it straight down.
Okay. So Kyle, are you sticking with your original thought, or are they convincing you? What do you think?
No, they convinced me. I think straight down is better now.
Okay. And I really like the way that Cade and Sally were explaining it there, that, Cade was talking about the components and giving that math sort of thought was really good. And I like just the practical way Sally said, like some of the force you're applying isn't really doing what you want it to do. And so that's like a super practical way to approach it as well. So it is true that while it would be effective, like that one pushing in and down, you would spin it. It would work, but you are wasting some of your force. Now, it might be a practical scenario where you need to actually be pushing in to keep the wrench from slipping off or something, you need to have that friction or pressure. But generally speaking, if we're just thinking about trying to generate the maximum amount of torque, we want to use a perpendicular force at the longest distance from the center of rotation and use as much force as possible. All right, so if we think about all of those things and combine them, here's the equation. And torque uses a funny symbol. It looks kind of like a fancy T, but it's the letter tau. Greek. And then force we already know, and we already talked about, the most force you can apply generates the most torque. So you want to maximize your force. And then the longer the radius of your, or the length of your lever arm, so you want to maximize the R value. And then for your angle, you want to think about how you can generate the greatest perpendicular component. And so the greatest perpendicular component will be at 90 degrees. But if you go a little more than 90 or a little less than 90, you're going to lose a little bit of force. But the closer to 90 you are, the better your result. And let's think about that a little bit. Some of you may not be as confident with your sine functions, but what's the sine of 90? 1. What's the sine of any other angle?
Less than 1.
Less than 1, right? So the only way to maximize it is to use 90 because the sine of 90 is 1. Everything else is going to be a fraction. And so you're going to have less than 1 times your force times your radius. So we want that 90 degrees. So whether we're less than 90 or more than 90, we're not getting that 1 value, right? We need the 90 degree, the perpendicular angle. Now the units for torque are Newton meters because we're taking newtons as force times meters, the length of your lever arm, times an angle in radians. And again, the radians are a unitless value, so we don't call it Newton meter radians. We just say it's Newton meters, but we need to use radians in our angle. Now, technically, you don't have to convert this one to radians. Okay, now for some of the things we talked about the other day, you would need to. For this one, technically you don't. If you do sine of 90 degrees and your calculator is in degrees, you're going to get 1. If you do sine of pi over 2 in radians, you're going to get 1, right? So as long as your calculator matches what you're putting it in as. So if it's in degrees on your calculator, you need to put it in degrees in the formula. If it's in radians on your calculator, likewise, put it in radians in your formula. Questions about torque formula? Yeah, Ethan.
What does this like torque do? Like what can you do with 1 Newton meter torque? Is that like a Newton at the center or a Newton at the outside? I guess I'm just a little confused on that.
Hold off on that for just a little bit. We're going to come back to that pretty soon, but torque, and this is where it's kind of confusing, and that's why I don't want to go too deep, but I'll give you a quick preview. Torque is a vector. So it has a magnitude and it has a direction. And its magnitude is going to be calculated using this formula. How much torque am I creating by using this force at this distance and this angle? What's the torque I can create? And torque generates rotational motion. So torque is an application of force to create rotational motion. Now, the direction of the torque is actually going to be perpendicular to the circle. And that's where it's like, wait a minute, what? But we'll get to that later. So for now, we'll talk. I'll just give you that preview that there's a rule we're going to use called the right-hand rule, and we'll learn how to use that rule, and we'll talk about why you use it and why it's perpendicular, and we'll actually demonstrate how it works. But for now, I just want to hold off a little bit on that. Anything else you want to ask about torque? All right, let's practice a problem. So, oh, sorry, that's just a reminder. This does summarize the 3 previous things. So the things that you kind of knew, longer lever arm, greater force, perpendicular, you guys came up to those conclusions. And we also, like I said before, torque is to rotation like force is to translational, but they're not a straight plug and play. Like you can't say torque equals MA. Okay, it doesn't work. You can't say torque equals force of normal force. Like it doesn't, it's not the same. So, but they're the closest correlation between the two types of motion that we have. Right, so here is the problem that we want to solve. So we have this rotating disc, but we have kind of, instead of a tug of war, it's a twist of war or a spin of war. Where we've got two people applying forces that are going to make it spin one way and two people applying forces that will make it spin the other way. So let's just start at 12 o'clock at the top of the circle and let's think about how effective these people are. So at the 12 o'clock position, we've got somebody applying 4 newtons of force. Okay, not bad. 90-degree angle, good or bad?
Good.
Good. Yeah, they're maximizing that 4 newtons, right? They're not losing any of it. 7 meter lever arm. Not bad, right? Pretty good. Yeah, compared to the others.
Best out of all of them.
Yeah, it's the best out of all of them, right? So that person's pretty smart. They're pushing at a longest lever arm length of anybody, and not the biggest force, but you know, bigger than some, and definitely maximizing it by their angle. So this person's got a pretty good result. And which way would that person cause it to spin?
Clockwise.
Clockwise. Now if we go to the 3 o'clock, this person is pushing with 8 newtons of force, pretty strong, twice as strong as the other person. They're pushing at a 140-degree angle or pulling at a 140-degree angle, better or worse? Yeah, not super wise. And a 1 meter radius or length.
That's a lot of damage.
Yeah, so really this is like the the strong kid that doesn't understand physics, right? They're really strong, but they're not quite getting what they should be doing to maximize their efforts, right? So they're buff, but maybe they need to take some more physics. All right, now we get on to the next one down here at the bottom of the circle. Okay, here, this person, 9 newtons, better or worse?
Strong.
Super strong. We got the guy or the girl that's in the weight room all the time. They're ready to pump some iron. Okay, 90-degree angle.
Yes.
They've taken physics. All right, 4 meter radius.
That's how you know someone's.
Yeah, I mean, they could do better, but they could also do worse, right? So not too bad. We'll give them a passing grade. And then we go to the last person over here. 2 newtons of force.
That's all right.
That's okay. Yeah, they probably need to get in the weight room. But 90-degree angle. Yeah, nice. 5 meter radius.
That's pretty good.
Yeah, pretty good. Second best of all of them, right? So, and let's go back to this one. This one's going to rotate it which way? Counterclockwise. This one?
Wait, counter.
Counterclockwise. This one?
Clockwise.
Clockwise. So we got these two kind of not as strong, but pretty smart, right? Pushing this way, so efficient, but not as strong. And then we got these two that are strong and maybe not so wise in their technique, and then not bad, right? So who's going to win this battle? Well,
Wait, which one is tightening and which one is not? Like,
well, it's not a bolt, it's just like a disc that's rotating.
okay.
So it's like instead of a tug of war on a rope, it's a twist of war, like they're seeing who can make the disc spin more. Okay. So if we want to try to find the total torque and see who's going to win this battle, we just need to use the equation and we need to define what's going to be the positive direction, what's going to be the negative direction. So here they're saying, well, let's make this one clockwise, let's make it positive, and counterclockwise, let's make it negative. Okay, they're just telling us which is going to be positive and negative. You have to define that so we know. All right, so we know the equation for torque, and we also can think about, well, torque is a vector, and we can add vectors, right? We have to add them as vectors, so we have to consider their direction. But for rotational motion, there's only 2 directions. It's either clockwise or counterclockwise. So it's either plus or minus. We don't have to worry about components of rotation. We do have to worry about components of the force that creates that rotation, but not the rotation itself. So if we know the torque of each of these 4 players and add them together as vectors, we should be able to get the final answer. And we know the equation is just the force applied times the radius length of the lever arm times the sine of the angle that they push at. And if we just plug the numbers in, since they've said clockwise is positive, this person up here at the top needs to be 4 times 7 times sine of 90 in the positive value. This person, 8 times 1 times the sine of 140 should be minus, right? It's in the other direction. And this one, 9 times 4 times sine of 90, minus again, because it's in the anti-clockwise or counterclockwise direction. And then the last one, 2 times 5 times sine of 90 plus, because it's the clockwise direction. So we add the clockwises because they're positive, and we subtract the counterclockwise values. What'd you get, Matt?
-3.142.
It's almost pi.
Yeah, it's pretty
It's
close.
so close.
This is a good battle. Like, they're gonna be going back and forth, and it's gonna be a very slight win for the strong group, right? Even though only one of them really knew much about physics, it appears, they were strong enough to still overcome that lack of
Got
knowledge.
carried.
Sometimes that happens. Brute force can sometimes win. All right, any questions about that one? So in the end, we know that it is going to spin in the counterclockwise direction. Making sense?
Yes.
All right. So the winners are the brutes. All right, so here's our last slide for the day. We'll wrap it up here. This is, I want to introduce this concept and just start getting it into your brain and start you mulling about it a little bit, but we're going to break it down more on Thursday. So it is the concept of inertia, but now speaking specifically of rotational inertia instead of inertia more generally. I hope you remember from Newton's first law, objects in motion stay in motion without changing their velocity unless there's an unbalanced force, and objects at rest remain at rest unless there's an unbalanced force. So that's the idea. But what property of matter gives it inertia? What property of matter gives that matter inertia? What property of the matter keeps it from accelerating so easily?
Friction? Mass?
Friction would be an outside force, but mass is an actual property of the matter that would determine. So if I have a small light mass or low mass object, it's easy to accelerate. If I have a large mass object, it's hard to accelerate, right? So here in this first part, they're reminding you back in the day when all we knew was linear motion. Inertial mass is the measure of an object's resistance to accelerate in a straight line or change direction. Because remember, velocity is a vector, so it might be changing in speed, its magnitude, or it might be changing in its direction. And mass is what resists that. So pushing a little VW bug is a lot easier than pushing an 18-wheeler, right? So it's a whole lot easier to start or stop the movement of that small car as opposed to the big car, all based on the mass. However, when something is rotating, it's not just about the mass. Okay, and I want to try to illustrate that a little bit here. Can I get a volunteer?
I volunteer.
All right.
I also volunteer if you need another one.
Yeah, I forgot to say what you're volunteering for, Johnny.
Uh-oh.
You're gonna be pushed
Have
around.
you ever had a sword fight before?
Oh.
Yeah.
Yo, I should have volunteered.
All right. So, all right, so Johnny,
man.
come over here.
Unfortunate.
So if Johnny was going to go into a sword fight,
Oh, this is gonna be
Back
high.
out a little bit.
if Johnny was going to go into a sword fight, and this was his sword. Now, these two swords are equivalent basically in mass. They have virtually identical clamps, virtually identical. There's nothing like tricky. I didn't like this isn't foam or anything. They're the same. Okay, so they're going to be within grams of each other in terms of mass. But let's say that this is the sword you have to use. Would you use the sword? Go ahead, take it. Would you use the sword like that?
No. I use it from here.
Okay, why would you use it from there?
Well, I want the weight in my hands so I can, and also farthest from the center so I can maximize my torque.
Okay, and so what are you going to be able to do with that sword in that position that you can't do if it was the other way?
Basically everything.
Fast.
Hold it up.
You wanna see some real speed?
Hold it up and
Not
swing
clobber
it.
their
I
head, but-
guess you can-
Yeah, and like you said, everything's going to be easier. You're going to be able to accelerate it, right?
Yeah.
Yeah, you're going to be able to accelerate. If you flip it around again, I mean, it almost feels like it's going to break, right?
Yeah.
It's
That's good for like.
it's kind of hard to accelerate,
A
right?
nice ball.
That'll do more damage.
Now, how about if I gave you this sword?
That one is cooler. Like, you can hold it in the middle, like.
Where would you hold that sword?
Right
Yeah.
Because if you hold it on either end, it's gonna be like that one at the opposite end. It feels like it's gonna break and I can't really maximize my torque. But here, I won't have as much torque as I would on that one, but I can evenly use both sides of the sword.
Yeah, good. So, I mean, just pretty practical. Are you a sword expert?
A little bit.
A little bit. Okay, great. I picked the right person. Okay,
Perhaps.
so.
I got a model master sword.
You go ahead and you can put that down. So, yeah, I mean, he sounds like a sword expert. He knows what he's talking about, and he applied the physics correctly too. Thanks, Johnny. So when we're talking about rotating something. Can actually do
I would have been.
No, I would be outmatched for sure. But with rotation of a sword, we're rotating it back and forth, right? You're spinning it around a circular motion as you try to block and parry and dodge and thrust and all. I don't really know, but the key is, though, just like you said, if the mass is located in one location, it's hard to accelerate it in that circular motion. If the mass is located in another area, it's easy to rotate it in a circular motion. And so it's not just the mass that matters, it's also where the mass is located. It's how that mass is distributed, right? And that's the idea behind rotational inertia. For linear motion, it doesn't really matter. I mean, if the truck's heavier in the front or the back, it doesn't matter. I still have to push all of it, right? But for rotating things, it does matter where that mass is. If it's centrally located, that's a lot easier to accelerate. If it's out on the edges, that's going to be a little bit harder to accelerate. Okay, so that's the basic idea behind rotational inertia. And then the final thought here in the tan part at the bottom, one of the downsides of rotational inertia is it has a lot of synonyms. And this is where a lot of students do get confused. Because in some books, you'll hear it called the moment of inertia, others angular inertia. We typically call it, I usually call it rotational inertia. But then sometimes, rarely, you'll even see angular mass and rotational mass. And those are a little more rare, but because it can be called so many things, a lot of times students get confused. Like, they know the equation. We haven't even learned it. That'll be Thursday. But they'll know the equation for it, but they won't know that that's what the question's asking because they're using one of these other synonyms. Okay, so that's one thing I wanted to get you in mind. I'll remind you of that. We'll pick it up here on Thursday and actually start looking at the equations for this calculation.
What is the units of inertia?
It's meters. Let's see. It's
Kilogram meters?
no, you take it's kilogram meters squared is the units. So yeah, it's an unusual unit, but we're going to dig into the units for it and other things later. So for today, we're almost out of time. So you guys in the Zoom, if you have a question, stick around. Otherwise, you're dismissed, and I'll see you Thursday. For those of you in here, since we're increasing our numbers, it's going to take, I have been just cleaning the desks myself, but now that we're increasing numbers, I'll just come around and kind of spray the tables off real quick. If you don't mind grabbing a paper towel and wiping it down for me, that'll make it a little bit more efficient. So as soon as you're ready, I'll just go spray down. You can grab paper towels are right there on the wall.
Oh man, this one. I know. It's so weird. If you
Try not to get you sprayed with this stuff.
Oh man.
Oh, that's half the day.
Dang.
Yeah, it's weird. School goes by faster. Having like classes like.
Yeah, the classes are slower.
But
Like they go on so
Yeah.
fast.
It's weird.
But like, we're almost done.
Yeah. Alrighty, thank you.
All right, yep. You guys enjoy your lunch.
Thank you.
Thank you. The paper towels are just over there on the wall now.
Thank you.
See you, John.
Thank you, Ms. Webb. Have a good one.
You too.
Like I said earlier, did you help with the,
Yeah, I'd be glad to.
I was having problems on the last two ones where you, because the number gives the coefficient of friction,
Okay,
and I was getting really confused because
all right, let me take a look at it.
I'm sorry for being late.
Thanks, Mr. Webb. You what?
I couldn't find the class.
Oh, okay.
And
You're
like,
welcome.
everyone told me to go into like multiple people, even my teacher from the previous class told me to go into like the second floor of like the building
Oh,
over there.
that's where most of the science
And I was
classes
just
are.
like, okay. And then like I was asking people in there, no one could help me. And
You didn't think it'd be that hard, huh?
yeah.
So it was the second to last one
All right. let me open it up here.
in the unit 10, yeah. Something about the circular motion is just difficult for me, but
Most students
Uh,
find this to be a lot more challenging.
yeah. 14 I was confused on, and also 13 kind of.
Okay. Your questions might be different because it generates a random assortment of questions. So
Yeah.
do you know which of these categories it would be from? I guess we can look and see if any of them look familiar.
Yeah, I'll roll definitely recognize it.
So did you get this one?
No.
This one?
I got that one, yeah, I think.
But you don't have a question about that one?
Not really.
Okay.
This was the one after the one I was confused on.
Okay.
Here, I can just show you right here if you need. It's the one where you have to determine the maximum speed there is determine the curve that's fitting. The coefficient between the wheels and the road is 0.65, and there's dry and 0.25 when the road is wet, right? And you have to find the centripetal acceleration.
Okay. Oh, then it's in this complete problems 3 part. Okay.
Yeah,
this
it's
one.
that one.
All right. Engineers trying to determine the maximum speed at which a vehicle travels around the curve that's getting. She knows the coefficient of friction between the wheels and the road is 0.65 when the road is dry and 0.3 when the road is wet. She knows that the mass of the vehicle does not matter, but completes her calculations for a 800 kilogram car. Answer the following questions for the case when the car is traveling at the maximum speed that will allow it to safely navigate the road both wet and dry. Should she
So-
perform her
So the first one I said wet because
Okay.
it's better over.
Yeah.
But I couldn't find the centripetal
In
acceleration.
this case, what is the car's centripetal acceleration? All right, so, okay, so the centripetal force would be the net force.
Yeah.
And the net force in this case, if it's purely friction that's allowing them, then the friction force and the net force would have to be equal to each other.
Yeah.
So if we think about the friction force being mu Fn, that's going to equal the v squared over r centripetal force.
Yeah.
And then Fn, since it's on flat ground, is just going to be mg. Just the mass
Yeah.
times acceleration due to gravity. And so that means these are going to cancel.
Okay.
And so you're going to have the coefficient times g equals v squared over r. And we want to, they're asking you for, well, for the centripetal acceleration, we need to find the v squared. Well, we can do it a couple ways.
Just to confirm, this is the formula for centripetal acceleration, right?
This is, so you could, yeah, you could actually say,
Okay.
you could actually say mu Fn equals MAC. So you can solve it that way. And then so mu mg equals MAC, and you know m. So mu times g should give you the acceleration.
Uh-huh.
So in this case, they had mu of 0.6, 0.3 if you're using the wet,
Yeah.
times 10 for g. So 0.3 times 10 gives you 3 for the acceleration.
Oh, okay.
And then in this case, what's the car's speed? So you could either go to this, or you can use this.
Oh, okay.
So if you know this is 0.3, you're looking for this, and then the radius gives you in the picture there is on mine, it's 150, yours might be different. But so you just solve for v.
Oh, okay.
I was thinking that they were gonna bring you down to this one where it's mu gr equals v and we square both sides. So that's the most common way that you use it. But this one there, this is probably what you needed on the challenge question. But for this one, that's this top part works.
Oh, okay.
Is that making sense?
I think so, yeah.
I'm not sure why they have so many things where they have you convert like to miles per hour stuff. That doesn't show up super frequently, but every once in a while, like it's kind of a pointless exercise. That don't really do that in AP college board, but
Yeah.
good practice, I guess, for conversions.
Thank you.
Are we gonna learn work and energy?
Next unit.
Okay, cool. I was just wondering if I should go look that up on my own, but.
Yeah, when we finish this one, not not this week, but next week we'll finish rotation. And so the week after next is when we start work, energy, and momentum. And that's really our last big topic. So we'll have those 3 weeks leading into spring break to learn about those 3 topics. And then when we come back, if there's anything I feel like we need to review, we will. And then the only thing left is simple harmonic motion. And they've taken away waves and sound and everything out of that. So it's basically just how does the pendulum work? And
Okay.
then, you know how we did like the mass on a spring?
Yeah,
It's
It's
just
just
that
that,
again. Yeah,
circular-ish.
yeah.
All right, cool. Thank
So
you.
we're getting close to the end here.
Yeah. Crazy.